Hello, Prof. Joe here with an example problem for a rectilinear motion with non-constant acceleration. Let's go ahead and get started. What I like to do is start my givens and finds and actually read through the problem again and make sure everything is written out, and so that we don't forget some of the pieces of information we're given. So I'm going to go ahead and write the word given and read through it. Particle travels along a straight line with a velocity of v equals 12 minus 3t squared. OK, just barely off the screen there. I think you can still read that. And that's in meters per second. Units are very important so we can keep our dimensions straight. We don't want to mix velocity, position, or acceleration, and keep those separate. T is in seconds. When t equals 1 second, is located 10 meters to the left of the origin. I'm going to do two things with this given. The first is I'm just going to write it down. The position at t equals 1 second is going to be equal to 10 meters to the left of the origin. I'm going to call that negative 10 meters. OK, now let's start our picture. All problems need a picture, even if it's a simple one. It can really help you. And you'll see in this one it's vitally important. 0 right here. And at t equals 1 second, I'm at negative 10. I'm to the left of this. This is t equals 1 second. OK, so now I started my picture. I've got a couple of my givens up. I'm going to keep reading. Determine the acceleration when t equals 4 seconds. Hey, it's asking me for my find. Find the acceleration when t equals 4 seconds. The displacement from t equals 0 to t equals 10, that would be the position at 10 minus the position at 1. You see how I'm already putting some hints on how I'm going to solve this problem right into my givens and finds. Actually, I just wrote that wrong. It doesn't say 1, it says 0. So the position is at 10 minus the position at 0. That's going to give me my displacement between the two. And the distance the particle travels during this time. I call that s sub t. OK, we got our givens and find, and we can get started. What I always recommend on any of these kinematics problems is remind yourself of the 3 base kinematic equations. I'm going to write those down now. I got space over here. We have, the first one is velocity is equal to ds dt. We have acceleration is equal to dv dt. And finally, the one that's created with the other two, ads equals v dv. If you don't have those 3 memorized, it's time to memorize them. These are useful in all of the kinematics we do. In fact, every equation we use in dynamics, directly or indirectly, comes from these 3. So you need to be able to just recall those very quickly. OK, and now I'm going to show you how you know which one you're going to use. Let's go with the first find, the acceleration at 4 seconds. OK, so we're going to look at our givens and that find to figure out which of these 3 equations we might want to use. In my givens, I have a v and I have a t. OK, so I'm going to need something with a v and a t. There's 2 of those. For my first find, I need an a. So there are 3 things I'm looking for, a, v, and t. Which equation has a, v, and t in it? Oh, right here. That's the one I'm going to use. So I'll go ahead and write that down. A equals dv dt. And that's going to be equal to the derivative of my v, which is 12 minus 3t squared meters per second with respect to time. OK, I can take the derivative of that pretty easily. The derivative of 12 with respect to time is 0, because 12 doesn't change, minus 6t. And it's now meters per second squared, because we divided a meters per second by a time, which is always in seconds. Negative 6t. Now we need to find acceleration at 4 seconds. Well, I plug in 4 for t. Negative 6 times 4 equals negative 24 meters per second squared. OK, we have solved our first part of the problem. The acceleration at 4 seconds is negative 24 meters per second squared. Okay, to give myself a little extra room, I just erased the board and I put the two things we found right here. We've got the acceleration with respect to time is -6t, and we've got the acceleration in 4 seconds, -24. Okay, next step. We need the position, which is s, at 10 minus the position at 0. Well, we need a position equation for that. How are we going to find a position equation? Well, we need s. We have v and t. Which of these three equations has those three variables? The top one, v, s, and t. That's the one we're going to use. So I'll go ahead and throw it up here. Velocity is equal to ds dt. OK, well, that's the derivative. We want to isolate s, so we're going to need the antiderivative. How we do that is I'm going to take the dt and multiply it by the other side, and we get v dt. That's going to be equal to ds. OK, I have derivatives here. I need the antiderivative, or the integral. So I'm going to take the integral of both sides. Now, many of you who learn integration in math class probably are used to integrating and adding a plus c. I really recommend getting familiar with adding your limits of integration so that you have both sides of the equation with all of the numbers that you need in. I'll show you how to do that. You always look at the variable, the differential variable you're integrating, and the limits have to match that. So on the left-hand side, I'm integrating in terms of, or I have dt, so I'm integrating in terms of t. So I need my limits to be in terms of time. You might initially think it'll go from 0, but we always want to use a point that we know something about. Which point were we given information about? Well, we know the position at 1 second is equal to 10 meters. So I'm going to go from 1 second to t. Now that top one, you might be tempted to put in a number for that as well, a definite integral. If you do that, you're just going to get a single number out. Equations are much more useful than numbers. So I actually put the variable t up there so we can get an equation for s and later plug in values to get whatever position we want. So I'm going to go from 1 to t. This lower bounds has to match the upper bound. The lower bounds in s has to match the lower bounds for t. So I'm dealing with s now. What is the position when t equals 1? Well, it's -10. And we're going to go to s. OK, first thing I'm going to do is I'm just going to solve this left-hand side, and then I'll solve the right-hand side. Then I'll put them equal to each other. Left-hand side, the integral from 1 to t of 12 minus 3t squared dt. That's going to be equal to, let's perform integration, 12t minus t cubed. Now I have to remember my limits of integration from 1 to t. OK, so I have to plug those in now, and we'll have, plugging in t, I get 12t minus t cubed. Then I have to subtract plugging in 1, which would be 12 minus 1. That's the left-hand side. It's equal to 12t minus t cubed minus 11. OK, now I'm going to do the right-hand side. The integral from -10 to s ds. Well, these are inverse operations, the integral and the derivative, so they cancel each other out, and the answer is just s. But I can't forget my limits. S from -10 to s. Plug in the s first, and then I plug in the -10, which is s plus 10. OK, left-hand side and right-hand side are both solved for. I'm going to set them equal to each other. And solve for s. I'm going to also put the t cubed in front, because that's how we like to order polynomials. And I have a -11, and I take that 10 and I subtract it on both sides, so I get a -21. And there I have my equation for position. Oh, I'm sorry. I didn't realize I was writing over some letters there. If you need a minute to catch up, go ahead and press pause. OK, so I have my equation for s. Now what? Well, luckily, right in my find, I put some intelligence. I know that I need to take s of 10 minus s of 0. I don't know either of those positions right now. So let's try s of 10 first. I'm just going to plug in 10 for t. Uh, 10 cubed would be 3 zeros. Negative 1,000 plus 120 minus 21. That's equal to negative 901, and that's in meters. Now, s of 0 is quite a bit easier. S of 0, well, we plug in 0 for both t's, and we just get negative 21. OK, so the displacement from s of 10 to s of 0 would be negative, you can still see that, 901 minus negative 21. OK, that is not negative 901 plus 21 is negative 880. And that is going to be equal to the position of 10 minus the position at 0. So that's our second answer. The displacement is 880 meters to the left. Okay, now we have to answer what was the total distance traveled during that time. Well, I just took the difference in positions. Isn't that the same thing? No, it's not. What I just came up with was the displacement. The displacement and total miles traveled are two different things. For example, if you were to drive to the store and back, your total displacement would be 0. You left your house, you went to the store, you came back. Displacement was 0. Was your total distance traveled 0? Well, no, it would be twice the distance to the store. So I'm going to go ahead and erase this board to get some more room. And I wrote down everything that we had solved for. I wrote down our new s of t equation that we solved for. Our answer, that s of 10 minus s of 0 is equal to negative 880. That's our displacement. I also wrote down the 2 points that got us to that answer, s of 10 and s of 0. One more thing I did is I actually erased the numbers I had on my number line. I didn't know what the scale of this problem would be when I started, so my number line, I have the 0 up here and the 10 way down here. I wouldn't have had enough room for negative 880. So I'm going to make a new number line. I'm going to put 0 way up at the front here. And I'm going to put my negative 10 somewhere down here. Actually, I'm going to put the 0 on the bottom. I'm going to put all of my positions in the bottom and all of my times on the top, just so I can keep those two dimensions separate and not get them confused. Negative 10 was when t equals 1. And let's put the other two ones we found too. At t equals 0, I'm at negative 21, which would be somewhere here. At t equals 0. And at t equals 10, I'm way down here at negative 901. Yeah, it's not to scale, I know, but that's OK. It's a useful picture. There we go. Now we have to figure out what was the total distance traveled. OK, let's do a little bit of investigating. We got to know what these equations mean, not just with numbers in them. So what's it doing when t equals 0? The particle at t equals 0 is hanging out right here on our number line. But which way is it moving? Well, to figure that out, we just plug 0 into velocity. Velocity of 0 is equal to 12 minus 3. I'm sorry, 12 minus 0, which is equal to 12 meters per second. That means it's going positive direction. It's going this way. At t equals 1, I could plug in 1, and I'm going to get 12 minus 3, and that's 9 meters per second. Hey, it's slowing down, but it's still moving this way. How does it get way down to negative 901? Well, obviously it turns around, and what do you have to do before you turn around? You have to stop. So we got to figure out where it stops. Where would it stop? When its velocity is equal to 0. So we're going to use this velocity equation and say that 0 equals 12 minus 3t squared, and solve for t. Negative 12 minus 3t squared. I'm sorry, negative 12 equals negative 3t squared. We can make both sides positive, and we get 12 is equal to 3t squared. Divide both sides by 3, and we get t squared equals 4, or t equals 2, plus or minus. That means that our plus or minus 2 seconds at plus or minus 2 seconds, velocity is 0. OK, how do I put that on my number line? Well, I don't know yet. I got to figure out where on my number line it goes. This just tells me where velocity is 0. I need to know what's the position when velocity is 0. Well, when is velocity 0? I don't really care about negative 2, because that's before my time started. So I care about the positive 2. I'm going to plug that into my position equation right here. I'm going to say the position at 2 seconds is equal to negative 2 cubed plus 12 times 2 minus 21. That would be equal to negative 8 plus 24 minus 21. And it looks like we got the negative 5 meters. OK, so somewhere right around here, negative 5, we've got t is equal to 2. And what happens at that point? Well, it turns around. It gets to 5, and it does a U-turn. And it goes all the way down to 901. This picture is what's needed to help us solve total distance traveled. Because now we have 2 segments to solve for. We have this segment here between negative 21 and 5. Then we have another segment between 5 and 901. Those are 2 different distances that we need to add together. For both of them, we're going to calculate it the same way. Where we end minus where we begin. Even if we get a negative number, we're going to treat it as positive because it's distance traveled. So let's do that. Where we ended in this first segment is negative 5. Negative 5 minus where we started, negative 21, is the same thing as negative 5 plus 21, which would be 16 meters. That first segment, we traveled 16 meters. Second segment, we end at negative 901, and we're going to subtract from that negative 5, which is equal to negative 901 plus 5. Okay, that's negative 901 plus 5 would be, what is that, 896? Okay, so it's actually negative 896, but that just means we traveled 896 meters to the left. It's still travel. So we're going to add those 2 together. We're going to take the absolute value of that and add it. So we end up with the total distance traveled is equal to 16 plus 896, which is equal to, okay, and that's 912 meters. We have our 3 answers. Okay, what I hope you take away from this problem is how to use limits of integration to solve your integrals, and also how to draw a useful picture to find the answer to your problem. Stop trying to memorize equations and plug them in. Draw a picture and see what's the physical thing that's happening, and how do I relate to this problem. Hopefully that was helpful.